Brandon, and this is a project with Eric Domain, and we are from MIT. So our project is called Algorithmic Transitions Between Parallel Pleats, which is a bit of a mouthful, but if you're familiar with representational design, you might also know this as a level shifter. So before we get into what it actually is, here's a bit of a quick motivation for why we're using this. This is a representational model, and there's a few different features. So for example, you might have an area that's super wide, such as the clothes or figure. And we also have figures that we might have features that are a lot thinner. For example, this figure is holding a scale model of a region. So you might need an area with very thin pleats, and at the same time an area with very wider pleats. And so somewhere we need a way to transition them. So this is what transitions between parallel pleats is referring to. In this case, it's quite easy. It's just dividing in half. But we would like to be as universal as possible. So for example, perhaps it's not 1/2, but you're dividing by some irrational proportion, or perhaps maybe they're not evenly spaced like this. So we would like to know in what cases are we able to construct such a crease pattern as this, and when can we not? So we will define a problem like this. So we have some crease, which we're going to call our x-axis. We then have two sets of parallel pleats. So these ones we'll call A, and these ones we'll call B. All these creases are parallel, meaning they are some constant angle theta from the x-axis. And we will define the numbers A1, A2, A3, etc. to be the x-intercepts of the first, second, third crease, etc. of the A and B. With this setup, the theorem that we're going to prove is that a locally flat-foldable transition exists if and only if the alternating sum of these x-intercepts is equal for the set in A and set in B. And we'll call this the alternating sum condition. So that's it. This one equation is all you need to know whether or not a flat-foldable transition exists or not. So this could be any sort of spacing. This could be even irrational spacings, or it could be, they don't have to be even. So it's very universal, as we'll see over here. So the way we'll prove this is we'll start by the necessity. Then we'll talk about the sufficiency of the alternating sum condition. We'll look at an implementation, and then we'll discuss some potential applications of this algorithm. So first, let's start with the necessity. So as a disclaimer, I'm not a mathematician, I'm an engineer, and some of the math is kind of hairy. So I am a big fan of these, I guess, maybe not rigorous proofs, but demonstrations, I'll say. So let's model our parallel pleats as something like this. We have a cut just for now because we don't really know what's going to go in here. But what we do know is that this face and this face need to connect, and this face and this face need to connect. If, for example, I'm going to read this, perhaps our pleats ended up such that this face is higher and they're no longer connected, then basically the altitudes are different, and there's no way we can solve this. No matter what happens in the cut, there's nothing we can do to fix this. So that's essentially what we're going to do with this necessity proof. To formally prove it, we're going to use generalized Kawasaki's theorem. So many of you are probably familiar with the normal Kawasaki's theorem, which is about the angles around a vertex. So generalized Kawasaki's theorem is actually, we take a path and we make a circle around some set of vertices, and we're going to intersect a bunch of creases as we do that. Then we're going to take a point on this path and subsequently reflect it over each crease. And we're going to reflect it over each crease that it crosses, and we expect it to come back to where it started. If it doesn't, that means whatever is in here is not flat-foldable. So if we take this point here, it's going to first reflect over all the points in A, all the creases in A, which we can express that as this equation. It's then going to cross the x-axis, which will change the y coordinate by a factor of -1. And then it's going to cross all the creases in B. So essentially, what we're going to expect is that crossing all the creases in A is going to yield the same x coordinate as crossing all the creases in B. So that gives us this equation. And if you look closely, you'll see that the alternating sum is in this equation. So basically, the generalized Kawasaki's theorem is equivalent to the alternating sum condition for this setup. And therefore, if the alternating sum condition is not true, then generalized Kawasaki's theorem is not true, and a flat-foldable transition does not exist. Therefore, the alternating sum condition is necessary. So sufficiency is the main challenge of this proof. So here's how we're going to do it. We're going to start with a 1 to 3 base case, and unfortunately we had to omit this out of the paper because it was kind of long. But essentially what we did is we do some stuff with similar triangles, and we use some law signs. If you're curious, you can come ask later, but it's high school math basically. Once we have a 1 to 3 base case, where basically we're saying that if these three, the alternating sums equal to basically the value of this one, we say that we can add 2 creases at a time to this until we reach any general 1 to n case, assuming n is odd. So we'll see how to do that. Once we have this 1 to n case, we'll then see how can we stitch them together to form some general m to n case. So for example, this is a 3 to something. So this is the roadmap of how we're going to prove sufficiency. So first, the way we're going to prove flat foldability for everything is we really have to brute force it. So we basically have to do the Kawasaki's theorem around each vertex. Oh, and by the way, we are neglecting global self-intersection, but anecdotally it does seem to work. But we're going to restrict ourselves to just local self-intersection or local flat foldability. So we basically create names for each angles. We create names for each length to help us know what's going on. And then we're going to do Kawasaki's theorem around each of these guys. And then we're going to do a Kawasaki's theorem around each of this. Then we'll require that this last one is on the x-axis and horizontal. If all those things are satisfied, so all those equations are equal, then this transition is flat foldable. And if you want it more detailed, you can read the paper. So this is our inductive step, going from a 1 to n to a 1 to n plus 2. The first step is to add these 2 creases at the end. And this is so bn plus 1 and bn plus 2. And they're going to be some infinitesimal distance away from each other. So as epsilon approaches 0, they're going to be lying on top of each other. If we do that, and we crunch the numbers again, using the constitutive equations from the last slide, we will find that flat foldability is preserved. So all the equations are still true. And the alternating sum is preserved, because bn plus 1 will be minus, bn plus 2 will be plus, and if they're at this exact same spot, then there should be no change. So this is not super realistic, because in actual crease patterns, we do not have creases that are infinitesimally close. But what we can do next is we can take this bn and this bn plus 1 and shift them together some amount to the left. So now they're no longer overlapping. Again, we'll use the equations from before, and you can read them in the paper, that flat foldability is preserved when we move these 2 creases some constant delta x. And the alternating sum is preserved because this one is plus, this one is minus, and they move them the same amount. So therefore, any 1 to n case that satisfies the alternating sum condition, flat foldable transition exists, because these operations do not change flat foldability, nor do they affect the alternating sum. So before we dive into the m to n transition, we're going to introduce a term called pivots. So what you'll notice is that for each of these creases, first of all, each of these semi-infinite creases end at a point, and that point connects to at least one point from the other side. So this guy connects to this one connects to a few, and so on. So we're going to define a pivot to be a point that connects to more than one point from the other side. So they're circled on green. This guy is connected to all these ones. This guy's connected to these 3, and so on and so on. The reason why we're going to call out these points in particular is because they can be locally turned into a 1 to n case. So for example, this crease, this point here is connected to all three points in A, and it's connected to one neighbor on this side and one neighbor on that side. What we can do is we can replace the creases that are with the neighbors with these 2 auxiliary points, x minus and x plus. Again, these are auxiliary, and we don't know exactly where they are, but we do have one equation that we know. We know because this is a 1 to n transition, we know that whatever these locations x's are, we must know that x minus a1 plus a2 minus a3 plus x plus must be equal to whatever the position of this pivot is. Essentially, we're using the 1 to n alternating sum. So basically this gives us, we don't know what these are, but it gives us an equation. So what we're going to do is we're going to induct by stringing together a bunch of 1 to n transitions. So suppose we are at this state where we are almost complete with our full m to n. And we're going to assume that this is flat-foldable. Then we're going to add this 1 to n transition, which is by definition flat-foldable because we position this xa plus to be somewhere that makes this point flat-foldable. Then we're going to somehow stitch them together and make our full transition this. So zooming in on that operation, here's what's going to happen. I have an animation. So first, the x plus, x minus, these are auxiliary, so we're going to remove them. Then we're going to show that this point and this point are in the same spot. Same thing for this pivot and this pivot. Therefore, we should be able to bring this chunk over to connect with this chunk. Lastly, we will show that let's see. So, for example, this point here used to be connected to x minus. We will show that now that it's connected to all these guys, it is still flat-foldable. Same thing for this point, this pivot down here. It used to be connected to this xa minus, and now instead is connected to some point here. And we will show that these creases are equivalent, and we can merge them together. So you can check the details in the paper. Oh, yeah, something like that. Okay, now let's take a quick look at the implementation. So I will switch over to. Okay, if you're interested in the code, you can scan this QR code and it will take you to the GitHub repository. So I'll give you a moment to do that if you're interested. Okay. So let's see. First of all, we never assumed anything about data, so we're able to change that freely, and it will adapt. So for example, this would be a expleted steep ridge, for example. We also have 1 degree of freedom, so we can change this, for example, to it'll look slightly different, not super important. Let's reset that. So to prove that the transition exists, we use the induction, but to actually generate it, we're going to use an iterative linear time algorithm. So I suppose this animation might make the most sense. So let me select a base. Yeah. So essentially what we're going to do is we're going to first build the graph. And at each time step, there's only you only have 2 choices. Either you move forward in B or you move forward in A. So we're guaranteed to finish in m plus n time steps. After that, we're going to propagate Kawasaki's theorem to just keep moving them around until all of them are flat-foldable. So in that sense, it's not too hard. Yeah, so you can play around with this website if you're interested. So now let's talk about some applications of the algorithm. As mentioned before, so one immediate application is in representational design. So for example, this is a figure where the heads are a little bit more narrow than the body, but not so narrow that 1/2 would be sufficient. So instead, we're going to merge the body, which uses 64ths, to 80ths. And the only way we can do this is if we use a generalized ridge level shifter like this. So for example, you would plug these values into the implementation, and it will generate this level shifter. Surprising application is actually in terminating dense bouncing. So for those of you who are not familiar with this, suppose we have a packing like this, and due to flat foldability rules, we are required to make these axial creases bounce out. So when these creases emanate from the points, it's going to hit another ridge. When it hits a ridge, it creates a new vertex, which is then going to require a new crease to make that flat foldable, so it's going to bounce around. And in some cases, this bouncing is actually infinite. And so this is, I stopped at some point, but you can see it's pretty not fun, and it's going to get really thin and not actually flat foldable. So what we can do instead is we'll pick some ridge, and we conjecture that you can actually pick any ridge. So for convenience, we'll pick this ridge here, highlighted in green, and we bounce all the axial contours until they hit here. Then we stop. Then we conjecture that these axial creases will end up in such a way that they satisfy the alternating sum condition. And so then you can just simply construct the transition and flat fold your crease pattern. So again, this is all left as an open problem, but we conjecture that given an axial polygon, so closed by the axis here, you can pick any ridge, and the axial creases will eventually bounce to that ridge. And we also conjecture that, again, that this will always form a setup such that you can apply this algorithm. But again, we leave this proof as an open problem. So with that, I think that's all I have to present. Thank you very much.
This is really cool. We do have time for questions.
Is there a notion of waste or efficiency? Is there any paper used up in this transition?
So let's see, for example. So there's no paper that would have been used, that would have not been used otherwise. So you can imagine if we decide to do something more traditional and keep the grid size constant, well, you're still going to need this whole space anyways. So there's nothing really being used that wouldn't have been used otherwise. Yes?
I guess related to that question, is there a bound on the width of the gadgets that you're using, or can you minimize them?
Right, yeah. So we didn't formally define this, but again, anecdotally, what it seems to be is that if you take a rolling alternating sum, so let's see, I have the example at the beginning. So this example, for example, if you take the rolling alternating sum, this one starts to go up by a lot, and then this one starts to go down by a lot. So something about that alternating sum is related to like the altitude at that point. So if you end up somewhere where on A, the alternating sum is really high, and on B, the alternating sum is really low, that's going to take up a lot more width. But yeah, we haven't formally defined that yet.
I thought it was kind of interesting that in your computational algorithm working from one side to the next, it sort of mimicked what one does manually. If you start the pleats and you just go, well, that's got to be flat, and then that's got to be flat, and it seems to follow the same thing as one would do intuitively.
Yeah.
The determination of dense bouncing is really significant, really interesting. I'm going to have to think about the ramifications of that, but that solves potentially a lot of problems.
Yes.
There was one slide where you were talking about the two overlapping creases, and then moving one of the two overlapping creases with an adjacent one. Could you have chosen one of the overlapping creases, say a mountain fold, and any of the other valley folds? Didn't have to be the adjacent one. You just choose a pair and move them.
Yeah, so I don't think so. I do think that they need to be, first of all, it needs to maintain the alternating sum. I do think that they need to be adjacent, but they don't need to be these two particularly. So you can move, for example, these two. But I don't think you can move, for example, like these two mountains. Because I guess as an intuitive way to think about it, the alternating sum is going to be plus for all the mountains and then minus for all the valleys. So if we're decreasing these two mountains, we're decreasing on the plus side, so the alternating sum is going to change. But if we so what's your question about this mountain, for example, this valley and this mountain?
No. If you, maybe I'm misinterpreting what the alternating sum is. If you move an adjacent mountain and an adjacent valley the same distance. Sure. How is that different than moving a mountain in any other valley the same distance?
Yes. Well, again, this is just a construction for the sake of proof. So it just suffices to show this, but it could be possible. Yeah.
Okay. Just make sure I understand.
Sure.
Cool.
Yeah.
So for any like instead of like those like parallel creases that you need to merge. Is the crease pattern, the flat-foldable crease pattern that generates, is that unique, or are there infinite ways to do it?
Right. That's a good question. So we actually have 1 degree of freedom, and that comes with that comes with so so we change this value, beta 0. It's basically going to change the angle of this first piece. So example, we change this, it's going to become slightly more shallower, or we can change that further. So we have this 1 degree of freedom when we are doing the Kawasaki on the first crease. But after that, it'll propagate down towards the end. So we have 1 degree of freedom.
More questions? Well, let's thank the speaker again. That ends this session and this day. Everyone head over to APC for pre-dinner drinks, and see y'all at the reception.